Good day, everyone. Our project is entitled Modeling and Simulation of a SCARA Robotic Manipulator using Kinematic Analysis and PID Control. The main goal of this project is to mathematically model the motion of a SCARA robot using forward and inverse kinematics, and then simulate its trajectory tracking performance using PID control in Simulink. In this project, we developed the kinematic equations of the robot, generated a desired circular trajectory, converted that trajectory into joint values using inverse kinematics, and then used PID controllers to minimize the tracking error of the manipulator. This is the complete Simulink model of our SCARA robotic manipulator. The model is divided into several main parts: the desired trajectory generator, the inverse kinematics block, the PID control section, the integrators, which represent the actual joint states, the forward kinematics block, and finally the XY graph, which shows the resulting trajectory of the end effector. First, this section generates the desired trajectory of the end effector. We use the clock block as the time input of the system. The time signal is passed to the cosine and sine blocks to generate periodic reference signals. These signals are then multiplied by gain blocks to define the radius of the circular path. In our setup, the gain value determines the size of the circle. After that, constant blocks are added through the sum blocks to shift the center of the trajectory. Because of this, the generated reference trajectory becomes a circular path centered at a defined position in the workspace. After generating the desired trajectory, the desired x, y, and z coordinates are fed into the inverse kinematics block. The purpose of inverse kinematics is to compute the required joint variables needed for the robot to reach a desired end effector position. In our SCARA manipulator, the outputs of the inverse kinematics block are θ1, θ2, and d3. In other words, once the desired position is given, inverse kinematics determines what joint values are needed so the manipulator can follow that path. The outputs of the inverse kinematics block are the desired joint values. These desired values are then compared with the actual joint values through the sum blocks, where the system computes the error. This error represents the difference between the desired joint motion and the actual joint motion. The error is then passed to the PID controllers, one controller for each joint variable. The PID controller minimizes the tracking error by continuously adjusting the control signal. After the PID blocks, the integrator blocks represent the actual joint responses over time. These actual joint values are fed back into the sum blocks, creating a closed-loop control system. This closed-loop structure allows the SCARA manipulator to follow the desired trajectory more accurately. Once the actual joint variables are obtained, they are sent to the forward kinematics block. The role of forward kinematics is to convert the actual joint values back into the actual position of the end effector. Specifically, it computes the x, y, and z coordinates based on θ1, θ2, and d3. This allows us to determine the actual motion of the manipulator after the effect of the PID controller. Finally, the x and y outputs of the forward kinematics block are connected to the XY graph. The XY graph shows the actual path followed by the end effector in the workspace. By observing this graph, we can evaluate whether the robot successfully tracks the desired circular trajectory. Normal operation. For the first test, we ran the simulation using the tuned PID parameters and the circular reference trajectory. As shown in the XY graph, the manipulator is able to follow the circular path. This confirms that the inverse kinematics, forward kinematics, and PID control are functioning properly as one integrated system. Transient response. The initial straight line portion before the circle is the transient response of the system. This happens because the manipulator does not start exactly at the desired starting point of the trajectory. The PID controller first drives the system toward the reference path, and after that initial correction, the manipulator settles and follows the circular trajectory. PID effect. We also tested the effect of PID tuning on the system response. When the PID parameters are not well tuned, the trajectory becomes less accurate and may show more lag or deviation. With properly tuned PID gains, the response becomes smoother, and the manipulator follows the desired trajectory more accurately. This shows that PID control plays a significant role in minimizing tracking error. As an additional test, we changed the trajectory radius by modifying the gain values in the trajectory generator. The system was able to adapt to the new circular path, showing that the model is flexible and can handle different trajectory sizes. In conclusion, the project successfully modeled and simulated a SCARA robotic manipulator using kinematic analysis and PID control. Forward kinematics and inverse kinematics were used to describe the robot motion, while PID control improved trajectory tracking performance. The simulation results show that the manipulator is able to follow a circular path, validating both the mathematical model and the control strategy. Overall, the project demonstrates that a SCARA robotic manipulator can be successfully modeled using kinematic equations and controlled using PID for trajectory tracking in Simulink. After seeing the Simulink simulation, we will now move to the MATLAB codes, where the core kinematic equations and trajectory computations of the SCARA robot are implemented. The Simulink model demonstrates the system behavior, while the MATLAB codes represent the mathematical foundation of the system, including kinematic modeling and trajectory planning. This test verifies the forward kinematics model. Given the joint inputs θ1, θ2, and d3, the program computes the end-effector position and displays the corresponding robot configuration. To validate inverse kinematics, the resulting joint values can be substituted back into the forward kinematics equations to confirm consistency. This test validates the geometric visualization of the SCARA manipulator using the computed joint positions. This test verifies the time-varying motion of the manipulator. By changing the joint variables continuously, the robot animation demonstrates the dynamic behavior of the SCARA model. This test verifies trajectory generation in MATLAB. A circular trajectory is generated using parametric equations, and inverse kinematics is used to compute the required joint values for the robot to follow the path. This test verifies the usability of the SCARA simulator by allowing the user to choose between forward kinematics and inverse kinematics operations. The initial straight-line portion is the transient response of the system. This occurs because the manipulator does not start exactly at the desired trajectory point. The PID controller first corrects the initial error, then the system settles into circular tracking. So overall, this completes our demonstration of the SCARA robotic manipulator. The results confirm that the system achieves accurate motion and effective trajectory tracking using kinematic modeling and PID control. Thank you.